Okay, so a few more physical properties. Buoyancy. Buoyancy is the upward force a fluid exerts on an object. It is a force. Do you remember our middle school definition of a force? Pretty basic definition. It's a blank or a blank? A push or a pull. Okay, so a buoyant force is going to be pushing a boat or anything in a liquid or gas upwards.
Gravity pushes it.
But what pushes it down? Good, the force of gravity, which would really be the boat's weight. Buoyancy pushes it up.
Thank you.
So if the forces do what, or if the forces are what, the boat will float. Equal, very good. If the force up equals the force down, then it balances out and it will float. What if the force of gravity is bigger than the buoyant force? It will sink. What if the buoyant force is bigger? It will go up and up and up and up and up and up. Now, eventually it will reach the point where it balances, though. It's not going to, the buoyant force won't make it fly. Because the buoyant force will decrease as more of the boat's lifted out of the water. And we'll talk about why here. Let me show you the video clip real quick. So Archimedes' principle is this principle that sort of relates to buoyancy. Why is it that boats, steel boats will float when steel is something that will sink? Well, Archimedes' principle says that the buoyant force, so the amount of upward force, that's the buoyant force, is equal to the weight of the displaced fluid. Okay, so what does the displaced fluid mean, Tom?
Where it could be, but it's not.
Where the water could be, but it's not. Where it's been pushed out of the way. We study the displacement method. When you dropped objects in the graduated cylinder and the water went up. Okay, well, if you put something in water, that means the water can't be there anymore. So the water is pushed aside. So if the boat wasn't here, the water level would be here and all of this would be filled with water. But with the boat in the water, all this water has to be pushed away. It has to be displaced.
Like when you put a water bottle in the water.
So let's instead of looking at a boat, let's look at you. This is you. Here's a completely full swimming pool, or you could imagine like a bathtub. And you cannonball in there. Maybe you just kind of gently get in there so you're not extra splashing. So you get into the swimming pool. Well, if it was completely full to begin with and you got in, what's going to happen to some of the water? It's going to come out of the swimming pool. It's going to overflow. It was filled to the brim. Yep. So now you're in there, so that means some of the water's got to leave. So this would be like the spilled water. My computer skills right here. So this is considered the displaced water. If you could collect all this water in buckets and weigh it, if the displaced water weighs less than you will do what? You will actually sink. If the displaced water, and water is pretty heavy. If you ever had to carry like a bucket of water, it's pretty heavy. So if the displaced water weighs more, well, I shouldn't say more. If it weighs the same amount, you will float. If it weighs more, then you're going to be like rising up. And then it'll reach a point where you're kind of balanced. And it will weigh the same. So if the displaced water, you got to consider the weight of it. If it weighs less than you do, the upward force is not enough. You're going to sink. If it weighs more than you do, then you're going to rise, and eventually it'll reach the point where it weighs exactly what you weigh, and that's where you just kind of float there. So this was Archimedes' principle. The story goes that he thought of this idea of displaced water and the buoyant force while in his bathtub, naked, and he just, eureka! That's how buoyancy works. And he, reportedly shouted eureka, running down the streets naked.
Really?
Yep. That's where the term eureka comes from. I'm blowing across the top of this piece of paper. I'm not blowing underneath it. blown across the top. And the paper rises up. So here's another property for you. Bernoulli's principle has to do with the velocity of a fluid. And Bernoulli's principle explains why airplanes work, why frisbees fly. It explains the property of lift. Okay, so this is yet another force, a lift force. But Bernoulli's principle says that as the velocity of a fluid increases, the pressure decreases. So there's air pressure pushing down that piece of paper. But the faster the air moves across it, the lower the pressure. So if you've got low pressure on the top, higher pressure on the bottom, what happened to the piece of paper? It's going to rise. Higher pressure will win out, pushing it up. So that's what we just did. The faster moving air across the top of the paper decreases the pressure. So faster means decrease here.
At a velocity.
The air below the paper, though, is now at a higher pressure, a greater pressure, compared to the air on the top. So you have the low pressure, high pressure difference, and the paper rises. Yes?
So is that like how you get like a water and you take the straw, take another straw and you blow over it really fast? It'll like spray out?
Oh, yeah.
What are you talking about?
But if you take like a cup and it's just got a straight up straw.
Yeah.
You take the straw and you can put it, the first one straight up, and then you take another straw and you put it parallel.
Yeah, perpendicular.
If you blow really, really fast air, then it'll actually like vacuum it out and it'll spray it.
Make a small cut and stick some rubber so that both the pieces are right angles. Place a small stem in the glass and blow from the other end, and you'll see a fine mist of water, like a spray coming out. You can see this in a close-up. It's a very, very fine mist, a spray.
Thank you. Yes, that would be the exact same thing. You are creating a lower pressure in the straw. In fact, so low a pressure that the higher pressure from the water underneath pushes the water out. Okay, thank you for that addition to the lecture. Similarly, fly, property of lift. If you imagine air moving across the top of a wing, and really it's not so much the air that's moving across the top of the wing, it's just the wing that's cutting through the air. So you just have all these little molecules of air, and a wing is cutting through it, slicing through it. Well, if you have, a bunch of little dots of air molecules here in front of the wing, well, the wing's going to pass through, and you'll end up with those little dots of molecules of air at the end of the wing. So it's like we're slicing through the air, and the air that started here, it's going to end up here as well. But in order for this air to end back where it was, it's got to travel around this wing. And if you look at the wing shape, well, it's sort of curved on the top. Which path to get from front to back is longer, over the top or under the bottom?
Over the top.
Over the top. Over the top is a longer path for that air to travel. So if I'm telling you that they still meet up at the same time, like you guys are running a race, but somebody's got to run more of the track, who's got to go faster, over the top or under the bottom? Over the top. So the air actually moves faster over the top of an airplane wing, also like a frisbee. Hence you get some lift. You get that low pressure on the top and a higher pressure on the bottom, and you end up with lift. So the air above the wing must travel faster than the air below because it's got farther to travel. So the air above must travel across the curved wing while the air below sort of stays almost still. So whatever air I had here, it ends up right here. But when that wing cuts through it, some of the air above has to travel faster than the air below.
Why did it say farther but it's still further?
Well, it is, that was simply my misspelling. This is pronounced further. It should be farther. That should be an A. My farther is always mixed up. Did I tell you the difference? We've gone over that? No. What is the difference between farther and further? Farther means an actual distance. Further's like, yeah, I want to discuss this with you further, like more in depth. Farther is an actual distance, like my house is farther away. A few more random physical properties now. Hardness. What is like the hardest material we know of? Diamonds, okay. Measure of a solid's resistance to scratching. Elasticity. Good, stretchy, rubber bands. Measure of a solid's ability to stretch but return to its original shape. So be careful not to say like silly putty. That can stretch, but is it going to return on its own? No, so it's not elastic.
I think the last is glass.
Because you can, well, yeah, volleyball's not a good example. You can sort of stretch it, like you sit on it and it would return. Brittleness.
Glass.
Yeah, glass. Measure of a solid's tendency to shatter upon impact.
Alright, next slide.
Did you know that not all glass is considered solid? Like over in Europe, some stained glass windows in churches that have been there for years and years and years and years are thicker on the bottom than the top because they're flowing down.
Oh, that's cool.
That's because the ink, that's on.
Malleability. Measure of a solid's ability to be pounded into sheets. So this would be like your soft metals are malleable. Aluminum is one. Of course, we pound that into sheets to make our aluminum cans. All right, and tensile strength. Measure of how much pulling an object can withstand before breaking.
Engage.
That'd be maybe more elastic. It's elastic. Well,
Silly putty. Rope.
yeah, I was going rope. Some elastic things, you're right, you know, would have tensile strength as well, like a bungee cord.